afternoon or good morning, everyone who is joining us today for our webinar series. Thank you very much for taking the time to join in and listen to us. We're going to give everyone a few minutes just to get settled in here. I'm sure you're all suffering from the same situation where we're living on our Outlook calendars 1 hour to the next, and we have to wait for one Zoom call to finish and then another one to start. So we'd like to give everyone a few minutes to join in here and get settled down. I can see quite a lot of people are now joining, which is great. Thank you all for coming. I'll give it 30 seconds and just make sure there's no one else turning up, and then we'll get into this. Okay, I think I've seen the counter slow down now, so let's make a start. I think that's enough timing after a minute to let everyone settle in. So welcome everybody, and thank you for coming along. This is part of an ongoing series of webinars that we host here at Synaptec, talking about applications such as wide area protection and control. But you'll also see from our website there's a big history of previous event recordings and YouTube links with the whole thing that's recorded here. So don't worry if you don't miss any, if you miss something and you don't quite get something, we'll come back to you after this and we'll give you access to the recording. And also, while we're in the middle of talking today, you'll see there's also the opportunity to ask questions. Now, you can do that through the Q&A buttons, and then we'll try and keep a track of the conversations going on in the backgrounds while people are speaking. However, if we can't address them in real time quickly enough, we'll catch these at the end of the session today, and I'll try and go back and summarize for everyone on the call if there were, say, popular or frequently asked questions that are worthy of deeper discussion. But in the meantime, please remember that we'll have everyone attending this call on mute. So please use the conversation function there to communicate with us and ask questions as we go along. So today, this is about enabling wide area protection with IEC 61850. And if I could ask Stephen to click forwards on a couple of slides here, we'll quickly go through this introduction, tell you who the panelists are, give you some idea about what's going on with the technology and also progress, although that's slightly tongue-in-cheek. Stephen's going to have some fun with that one for you. And then we're getting into a kind of a panel discussion and a more interactive session where we're going to combine updates and information about some live examples of these deployments, as well as encouraging some polling and response from the audience to find out what your views are about the opportunities and limitations of this technology. So on the next slide, if Stephen, you'd move along, you can quickly see there's Stephen. Dr. Stephen Blair is our head of power system technologies at Synaptec. And unlike Stephen or Andrea, I'm not an expert, but I am here to help out with any questions about customers and deployments and the commercial side of things. But we're very happy to welcome Andrea Bonetti here from Megger, who's Megger's senior application specialist when it comes to protections and relay schemes. That's very important for us because Andrea was actually helping out with a project we've recently completed with our friends at SSE Networks, the transmission operator for the north of Scotland, and we're going to be exploring with them what was going on in that project in a little bit more detail, because it's a very good example of wide area control and protection systems. It's also a good example of how we establish interoperability with multiple vendors through 61850. So to set the scene a little bit, and before we get into the conversation, if I click on the next slide, some people I noticed in the registrations today are relatively new to us, or we are new to you. And so I wanted everyone to recognize that the thing that is probably most interesting about Synaptec's technology is that we invented and patented something pretty simple to understand. It's passive distributed sensors. We can measure any combination of things like current, voltage, temperature, vibration and strain over wide areas using sensors which are now totally passive. That means you no longer need a lot of civil works, power supplies, telecommunications infrastructure, copper wiring, or even synchronization outside of the substation in order to have a live view of something happening somewhere very remote or very inaccessible. So this is a technology where passive sensors network together by light, not by data, outside over very long distances. So it's ideal for wide area applications like control, protection schemes, or also condition monitoring. Now, having said that, that covers a very wide story. So The reason we've got a business, if you want to click onto the next slide, Stephen, is pretty simple, and I won't spend time on this because I think there are more experts here than me who really know what they're talking about. As our world goes from burning fossil fuels to create energy centrally, we're moving to a decentralized and digitalized network that we all recognize, and we're moving from a radial to a meshed network where there are lots of challenges coming along about how you integrate renewables without destabilizing the grid, without causing problems for protection and control over wide areas. There are lots of discussions, and in fact, Andrea and I were both at the DPSP conference recently, a couple of weeks back in Newcastle, where there was a very strong theme about the limitations now in modern networks of distance protection and why differential protection would be good if only we could get over the problems of variable latency and issues with switch packet data over IP networks causing a problem. So telecommunications and sync being a challenge in the modern world. But as we move from thermal generation towards a renewable supply, and we want to maintain availability and resiliency of our grids, maintain safety. Clearly, there's a role to play for Synaptec with distributed sensing. And indeed, on the next slide, you'll see overall, these are typically the kind of applications on the next slide here that we get into with digitalizing substations, monitoring cables and overhead lines in very remote locations, renewable grid connections, which is one of the case studies we'll look at here. And also top right, you'll see there's a growing part of our business helping people to manage complex circuits with multiple feeders and multiple branches where you've got some significant challenges with protection and control. So with that in mind, and having set the scene on why the industry is going this way and how we fit into it, Stephen wants to take you through a couple of slides and then some polling questions about what the considerations are around protection over wide areas using 61850. Stephen?
Great, thanks, Saul. So what I wanted to do is, I didn't want us to turn into too much of a history lesson, but I thought it'd be quite fun to look at how the technology in the industry that we work in compares to some other high-tech industries. And so I'm not going to take this too seriously, but I think it's quite interesting to look at this. So one of the obvious things that we all use every day is mobile technology, and this is the kind of generation of phone that I started off with, and it was quite good at the time, but in terms of computation, it's pretty limited compared to what we had today. The initial versions of that didn't really have any options for data, but then within relatively few short years, the technology changed quite radically, and today, if we compare that same the modern equivalent of that, it's much more advanced in any number of different ways, including like the number of transistors used in the main CPU, the data bandwidth that's available, and sort of raw computational power. So you can take almost any metric that's involved here, and it's gone through something like 1,000-fold improvement in terms of the numbers. Although the one exception to that would be battery life, which has actually probably declined over time just because that hasn't seen the same revolution in terms of the technology advance. So another area that everyone will be well aware of is the area of machine learning and computation. So that's also taken quite a radical leap. So sort of the late 90s and late 2000s, there were some sort of benchmarks introduced to allow the performance of different analysis techniques to be compared. And a few years later, there was quite an impressive paper which used some existing techniques that were well known using neural networks. But they figured out, the innovation here is they figured out how to do that computation efficiently using GPUs. And they're able to absolutely destroy that competition and win it outright. And then later on, after a few iterations of this, to even provide an even more impressive automated capability to analyze these benchmark data sets. And in parallel with that, we've also had DeepMind working on some quite classic, complex problems, such as the game of Go, and one I'm also a fan of, which is StarCraft 2. These are quite well known as being challenging, and lots of possibilities and very strategic games. And AlphaStar and AlphaGo were able to beat the best humans at these games and do astonishingly well. A little bit less frivolously, though, the same approaches were used for AlphaFold, AlphaFold 2, which did a much more useful thing, which involved sort of simulating protein folding. I'm definitely not a biologist, but from what I understand from this is that it takes something which is now relatively trivial to compute, but previously would have taken an expert with the right kind of X-ray imaging gear. It would take them a year to achieve the same sort of experiment, which can now be done in simulation quite easily. And so this has quite profound implications on things like when proteins fold incorrectly, for example, that can be the start of a disease. So this opens up lots of avenues for treating diseases, and I'm very much looking forward to living forever as a result of this work. And also something else I use occasionally, which is GitHub Copilot, which auto-completes coding, programming language stuff, and it's very impressive how well that works. It's kind of spooky how accurate it can be at predicting what you want to write in code. So these are some quite impressive trajectories for these different areas of technology with hardware and software. So if we compare it to the industry that we work in, which is sort of digital substations and power system protection more broadly, about 20 years ago, we started off with what I describe as a bunch of grey boxes, really. And in that same timeline, that has advanced to what also looks like a bunch of grey boxes. They're a bit nicer looking maybe, and they've got bigger screens, for example. But largely, it's not as significant a revolution as we've seen in other areas. However, there are some other developments that are noteworthy, and particularly standardization, which is underpinning a lot of what we do. Wide area networks are becoming more possible and to deliver phasor measurements, and new technologies like merging units and MPLS and time sync. These are all emerging and quite important and quite useful. But yeah, I'm obviously being a little bit facetious here, but this is how the technologies compare. Andrea, is there anything you'd want to add on that, on like the importance of some of the standards that you, from your experience? Oh, you're on mute, Andrea.
Yeah, sorry. Yes, I think it's an interesting picture that you have shown, how we didn't manage in the relay protection and community to have the same acceleration, which maybe also we don't even want to have the same acceleration because we are very careful in the changes. But what happened in the beginning of year 2000, the end of the 90s, is that we had a mess, definitely, in the digital technology applied to relay protection community because we were not interoperable. And this was jeopardizing all the concept. We invented the microprocessor, we put the microprocessors in the relays, etc. But every firmware, even from the same company, was not able to talk to the previous firmware. Different companies were not able to talk together. So our progress in these 20 years, yes, has been actually the capability to manage a standard, to have a standard and understand that this standard was the way to go, which is IEC 62050. So this is our jump, our step forward that we have done these 20 years. But I agree that the boxes are still digital computers, and we didn't reach that gap that was able to be reached in the other applications. I agree on that. Maybe it's good that we have like that, and we continue now with the standard.
Yep, yeah, I totally agree. That I think it's underappreciated how important that foundation of 61850 is for, and we'll continue to benefit off it in the future. So if I jump forward to the next slide, this will force some audience participation. And what we'd like to do is pose this poll question to everyone in the audience. And this is kind of based on what the previous slide, we're looking at technologies and how that's changing. So what I've suggested a few options here about where power system protection could see some radical changes, and where the audience thinks we should be focusing these changes. So I've suggested some things here about maybe better performance, wide area networking with higher bandwidth, low delay, better time sync. I mean, I think we already have the technologies, but they're maybe not being applied day to day for time sync, or perhaps more computation, maybe at the substation, at those nodes, or perhaps in the cloud. Maybe aside from technology, maybe we actually need better testing approaches, or maybe we need to use some of these processing capabilities to provide more enhanced testing, so that we can find unusual scenarios that we typically don't find through type testing or application testing scenarios. Or maybe, as Andrea was saying, maybe actually we want to slow down with power system protection because it's so critical, and we want to use things that are safe and are well known. So I certainly wouldn't blame anyone for selecting option 5, because I think that's quite a sensible approach. So while I've been talking away there, I think we've had quite a lot of responses to the poll so far.
Yep, so I'll just stop the poll there for everyone, and thank you all for participating, because most of you have actually answered now, so I can give a kind of snapshot of what that means in terms of the orders we received. So 10% of you said no to number 5 there, use trusted existing technology. Next most popular was grid edge or cloud processing. Joint second would be more advanced testing approaches and precision time sync, but by far and away the most popular response is number 1, meaning that, you know, what radical changes need for future protection? It's that high performance wide area networking requirement.
That's interesting. That's good to hear. I think that there's an appetite for wide area, whether it's for protection or system control. Yeah, I totally agree. It would be great to have developments in that area.
But it was, are we commenting, or you go on now? Or
Oh no, but please comment.
it was interesting. Did I well understand that the number 5 was the most voted? No, use existing stable trusted technology. No, the least. Good, the least. High performance wide area networking 64, precision time sync 450. I expected that, but I understood the opposite. That's okay, because I understood before that they use a trusted technology for the most voted, and I say okay, but we cannot. We cannot protect the new network with the old technology. We have to accept that technology has to grow. We may grow carefully. I fully understand that. We have to be careful, but we have to change the technology, accept it, especially use a standardized technology. High performance wide area networking and precision time synchronization. Pick up the most important points, I would say.
Yep, and yeah, if there's probably certain things we've not thought of as well. So, you know, feel free to leave comments or questions. Anyone in the audience, if there's something that we should be considering here that's not listed. So I think what I'll do is I'll move on to the next slide. So I just wanted to spend a couple of slides giving a little bit of detail on the projects that we've produced and installed for SSE networks, as Saul mentioned earlier. And this is where Andrea joined us as a consultant to help us test and validate this solution. So the challenge that SSEN had was that the conventional methods for protecting circuits, particularly relatively complex circuits where they have to connect make a new renewable connection into the system, and they need a 3-ended differential protection solution. That using conventional technologies, there's lots of headaches and costly elements in actually delivering that. In particular, they need reliable communications between all 3 locations. and that's difficult to achieve. Of course, it can be done, but it tends to be expensive to do, and you need lots of dedicated boxes in each substation to do that. You know, multiplexers or MPLS relays or whatever's used for that. So it ends up being quite an expensive solution to install and to maintain. So where Synaptec came in and where we kind of met this challenge was by using our passive sensing technology, so that all we need is a fiber to visit all 3 locations, and there is existing fiber that we could use for this. And we can passively collect all of the measurements and bring them into a central location. So just at one of those substations, we have our IED, which we call our interrogator, and it's able to see all of the measurements and get all of them instantaneously, you know, aside from the speed of light in fiber. So effectively, within less than 1 millisecond, we're able to deliver sampled value data, 4 kilohertz from all of those 3 locations in this case, despite being over, you know, 30 kilometers away. So this gives us a unique capability to be able to deliver interoperable data streams, but at a much lower cost and lower overhead. Anything you'd want to mention on the commercial side of that, Saul?
I'll add a couple of small points because I think it's of great interest. So we use this example because this is very typical of a transmission operator dealing with a queue of renewable grid connection requests at large scale. These are big industrial schemes. And of course, the economic preference is to tee off of an existing feeder to connect those renewable generation sites like a big wind farm, rather than trying to build new circuits, because whether you use pounds or dollars or euros, it's millions per kilometer, right, to build new HV lines to these remote locations. But in this case, up in the Scottish Highlands, this is a good example of where you'd have a renewable grid connection teeing off and creating these multiple branch circuits, where of course the distance protection scheme would suffer with overreach and underreach to identify where the problems are. But also, most importantly, in this case for SSE, these substations are remote and telecommunications infrastructure is not ideal. And also that always correlates with where the grid connections come into a country. An offshore wind farm is always going to connect somewhere relatively remote and difficult or inaccessible. So telecoms is a challenge. And then also, if these are older substations at the remote ends, you've got the additional problem that even if you wanted to deploy 61850 in a traditional sense, you're putting all of the telecommunications and power equipment, clocks in all those remote locations. Sometimes there just isn't the space. These buildings are old, and the civil works required to rebuild or build out that capacity to house everything, that's a significant cost. So if you can eliminate the civil works, the buildings upgrade costs, and the telecommunications infrastructure costs, you would be able to realize capital cost savings of around £250,000 or euros in a typical example like this. So these are significant enablers of superior protection schemes, despite how inaccessible and remote these locations are.
Yep. Okay, thanks. So this is what the schematic of the system looks like, but in real life, it looked a bit like this. You can see the panel built up with our interrogator IED, and we were providing sample value data to various other protection devices from multiple vendors. So a significant part of this project was actually to prove the interoperability with these other vendors, which we've done, particularly with Andrea's help. When we did our FAT for this system, we did a 3-ended system like you're seeing here on the screen. And that was actually over 50 kilometers of distance in total. For the actual installation, which I'll show in the next slide, we installed this in two substations here in Scotland, and it's just a 2-ended scheme for the trial deployment, but they're still 30 kilometers apart, and we're providing the data for differential protection over that long distance, and again with no power supply or time sync or any other auxiliary equipment required at these substations, just one IED at one location where it's convenient to have. So this is currently undergoing some long-term testing on SSEN's network. It's a 132 kV circuit. So we installed it last year, and SSE are looking to see how it performs over a two-year period, in particular over 2 winters, basically, with the hope that well, not a hope that we'd see a fault, but if there is a fault, it's likely to be during the winter. So that's the status of that, and it's operational right now, and we're kind of looking forward to seeing how it performs. On that system, do you have anything you want to add, Andrea, just from your observations from being involved in this?
I can only comment maybe because it took also for me a lot of time to understand how all the system works. That one of the key points, at least, is that the sensors, the remote sensors connected to the fiber, are fully passive, and this well, I took some days for me also to fully understand that it's really passive. You get voltage current transformer connected to this box, and the box delivers the current somehow to the main central station. And the efforts we did, and the beauty of all of this is that no matter which kind of protocol you're using, analog protocol to understand the currents, at the end you deliver them in IC650 format, the sample values format. So the interoperability communication level is there, which is beautiful, and also the interoperability, functional interoperability, which is something we have been concentrating very much. We have all of this system is in principle a merging unit, so it has a transfer performance, and they may not be liked by the protection relays that have their own algorithm based on the transfer performance of analog input card and current transformer, so it can be slightly different. So we really tried to do a lot of the tests to make this failing, because we wanted to make sure that we try every possible test, full load from left to right, and the sudden bolt into the left with the reverse, high load reverse, and low load reverse. We tried all the most difficult tests we could manage to do, but it was working fine, I have to say. Impressively working fine.
Yep, thanks very much. Yeah, it's really important, because this is a slightly strange new technology, but we did a lot of testing to make sure it is stable. And yeah, in particular, when we perform the protection on board our device as well, which is another option that we have, we did a lot of testing to make sure that the protection is operating correctly and not maloperating during these unusual conditions.
If we trip unwanted in the next month, which is always possible, of course, if we have some issues here, I still sleep well, because I feel that we have done really a number of tests that more than that we couldn't do. So everybody can make mistakes, but I'm pretty sure we have tested very heavily.
Yeah, great. Okay, so I'll move on to the next poll question. So as we kind of hinted at here, we're seeing that distance protection is going out of fashion a little bit, and the best solution, the best alternative to that is differential protection, which is what we've deployed in this system. However, one of the main trick to getting differential protection to work and to be stable is to have reliable time synchronization. Whether it's using PTP or discrete GPS units at each end, or GNSS units, or using the ping-pong approach across the network. There's lots of potential headaches with that, whether it's jamming of satellite signals or network asymmetry or jitter. So this question really is about how much does the audience agree that time sync is really the biggest problem for protection? And so there's some options here about, yes, that is 100% the main issue, or number two, where that is one of the issues, but there's other important factors too. Or maybe you're of the opinion that actually the time sync technology is already doing what it should be, and there's other things we need to focus on. Or of course, the standard response for this type of question is it depends, which is an acceptable choice also. So looks like we've got quite a few responses already.
I can stop that there if you like, Stephen, because I think we've got about just about 70% of people, most people have now responded, so there's no more coming in. If I freeze that, the outcome of that poll is, okay, there's only 4% of people who say that depends. I'll just quickly share this with everyone because it's easier. And then you've got 9% of people saying, you know, sync is not an issue for us, followed by, okay, a strong agree or agree, which are very closely matched, saying, okay, there are some other significant factors, but yes, reliable sync is critical. And I guess the point about that is that the picture that we were showing you before of those two remote sites, they could be 20, 30, or even 60 kilometers apart. The only thing connecting those remote CTs is optical fiber and colors of light going to and fro within the fiber. And that's important because that means we can capture all of the information from all those sensor networks centrally at one point, and then we process, timestamp, and publish one central stream. So we don't lose relative sync even if there's an outage anywhere in that system. And the only thing connecting those remote sensors to and fro literally are colors of light, and therefore there is no data outside of the substation and no kind of IP packet switching or latency challenges happening within the system. So it's one thing that we noticed is very important to the industry, is that we can pick up on that and make sure that we've got that centralized single point time stamping and publication of data.
Yep, okay. So it sounds like broadly the audience agrees with this statement then, that time sync is at least a major factor for securing protection schemes. And it's the kind of underlying factor that allows differential protection to operate. So having a method of kind of providing that inherently within the sensor medium kind of solves a lot of those headaches. Okay, so there's one last poll question here. This is our third and last poll question for the audience. Again, this is another slightly provocative question, but we have a well-known profile, 61850-9-2, which is the LE or light edition. And what we're saying here is that LE was an extremely good idea and very useful for aligning the industry and ensuring that we had interoperability. But maybe now we've kind of outgrown that and we need some more options. And so the choices here in the poll question are, yes, that we definitely need much more flexibility. I think a lot of people don't realize that LE itself isn't really the standard. The standard is much more flexible than LE and allows you to do practically anything with your data sets. Or option 2 is quite a good compromise, I think, where IEC 61869-9 provides a solution for more flexible data sets in a sort of structured, standardized way. Or maybe you're of the opinion that LE actually it should be maintained for quite a long time because a lot of work has gone into making sure it provide interoperability with that, and that's very successful. And if we change to something else, then we're at risk of losing that interoperability or having to start again to some extent. Or maybe you've got another opinion, in which case we've got another option there to select.
We'll give everyone a few more seconds to answer that one, Stephen, because I was letting you speak and digest the options here as people start to reply. So we're just getting over the halfway point for the audience now with some results coming in. Okay, so if I think we're probably running out of C1 responses there. We're at about 60-something% there. So if I freeze that where it is, now people have the time to think about their answers, Stephen. It's a pretty clear split between the yeses at over 70% and no's being very, very low, like 10% each.
Yep. So that's quite aligned with the earlier question about the technology kind of roadmap. So obviously the audience here are quite enthusiastic about using new technologies and being innovative, which is good, because that's kind of how I see things as well. Of course, we do have to be careful about interoperability at the same time.
Yeah, maybe we need to have some discussions also.
Yeah, definitely. I think these are all kind of quite deeply technical topics that could support an entire webinar on their own. But we'll kind of skip on to the sort of the last slide that we're going to use. But again, this is intended to be provocative, and what we're providing here is a bunch of statements about how we see protection at the moment and how we see it evolving in the near future, and what some of the issues that we're observing are. So just to quickly sum these up. So for example, phaser-based protection has been the norm for a long time, but perhaps with a massive proportion of converter interfaced generation, and maybe even a purely converter-based grid, the kind of waveforms that you might see during a fault might be quite radically different to what we're used to for a standard fault response. So maybe like a phaser-based approach isn't suitable anymore. I'm not sure about that, to be honest, but I think there's probably some research to be done there. Moving to the right here, is that substation digitalization is happening slowly. I think there's definitely lots of success stories out there and quite a lot of testing, but in terms of implementation, it's maybe a little bit disappointing that it's not, the new technologies aren't getting out there as fast as we'd hope. But that's just sort of the nature of this industry, where it's very risk averse. As we've already mentioned, distance protection, it's becoming less effective as networks are getting more complex, and it has issues. It's very difficult to specify the settings and to prove that those settings are correct. It's much more complex than than differential protection. And if differential protection is available, then that is always going to be favorable. So some other points here, distributed generation or distributed energy resources. Certainly in the Great Britain power grid, they have a significant impact on system stability whenever there's a major frequency event, such as what happened in 2019. The tripping of this generation is well understood, and we know why it happens, but it is a mal-operation, and it makes the situation worse because we're losing lots of generation from the system. So perhaps there's maybe communications enhanced approaches to improve that, or generally greater visibility of the system would help. Another 2 points that are kind of related here is that we could benefit from user engagement, so that the TSOs and DSOs who are actually using these systems ultimately, we need to get their feedback and understand their needs and share results of innovation projects that we do, like we've done with SSE networks. I would also say that from some involvement in standards committees, the representation of utility experts is pretty low, which is totally understandable because they're extremely busy. But ideally, we'd have lots of utilities engaging in those committees and telling the standards committees what standards needs to do. But at the moment, there's relatively few utilities who are properly engaged in that. And then the obvious thing to mention is that cybersecurity is a huge headache, I think, for everyone. It's complex topic, lots of different standards, different national standards, some international standards also, technically difficult to understand and achieve. So lots of complexity around that, but it's also very important. So that was a quick summary of what's on the slide here. Maybe Andrea, you could probably talk at great length about any of these topics, but is there any particular area you'd like to to focus on?
Yeah, my first thought is I want to define myself first, that I was writing it down. I'm a conservative, innovative, which I want to say that, okay, you don't have to risk, still you're a protection engineer, and majority of us here are protection engineers, so we don't want to risk to open the circuit breakers, or not even risk not to open the circuit breaker at all. But we have also to run and accept the new technology and the standardization. So that's why I say conservative, innovative. And for this, if we want to use a new technology, even if standardized, we need the user engagement, and we also need the utilities that are driving the standards. As you say, this is unfortunately like that. The utilities are not very much populating the really smart grid protection standards. I would say, though, maybe they are in some other standardization committees, but not very much in relay protection standards, and we need them. So I would concentrate on this. It's very important to accept that we don't know everything. You have to accept that we have to build the things, to understand things, and only by building things and by making experiments, and we can give data to all the community to improve standards or improve the technique. The rest are, of course, all the points you mentioned are very important, especially cybersecurity that we pretend not to see. Face-based protection, new technique may give us needs and also possibility to have different algorithms. But I would concentrate on these two at the moment.
Yep, I totally agree. Okay. There are a couple of questions.
Yeah.
Stephen, could I suggest actually on your slides, if you move forward 2 slides into your appendix deck, there's a slide which explains how it works. And a couple of the questions that I've been answering in the Q&A in the chat were about this, and we probably are guilty of using some acronyms that we shouldn't have just dished off because they're, you know, it's English language, and not English is not the first language of everyone on this call. So to recap on those questions, and I hope this is clear for everyone, the idea is that we actually use these industry standard CTs and VTs. They'd look the same if you saw products from GE or ABB or Hitachi Energy. They're very standard industry devices. The difference is that what connects them back to that central location where we have our interrogators is just a pigtail of fiber. So we're passively converting an electrical value like current or voltage into strain, which changes the reflection of light in the fiber that these things reflect back. It's a single-ended system, and the fiber that we're using was already available in the network, because typically what we find, certainly here in Europe, is that any power network over about 66, certainly 100 kV, has optical fiber available built in along the lines, and it's typically wrapped around what we call the OPGW, or the earth wire. This is the optical ground wire running along the top of the circuit. There could be up to 72 cores there. Whether those cores are dark or already in use for SCADA type traffic or telecommunications type traffic for the operator, we can use those fibers to reach out very long distances, and we can see up to 60 kilometers per fiber, where you can get 30 of these measurements taken. That's why the example that Stephen shared with you with SSE, where we can go one direction, one branch 20 kilometers, then another 30, we could have gone further. That can all be dealt with by one centrally installed interrogation device. But clearly, each one of those interrogators can manage a core of fiber and up to 30 simultaneous measurements. If you need to do more than 30 over a very complicated wide area scheme, we just take another fiber and another rack unit and just build up the size of the rack so that you can connect them. But again, that's the point. The connection between the central box that's inside of the firewall and the data network and the devices, the passive sensors which are outside, the only connection is different colors of light going through that fiber. So it's very important to emphasize that in this system architecture, there is literally outside zero data, zero power, zero copper wiring, zero IEDs, zero equipment or that's active electronics surrounding the measurement device itself. And also those devices, we should say, could be primary connected, like the pictures you see here, or they could be secondary connected which some customers ask us to do to take advantage of the fact that they've probably got CTs and VTs at the substation end, and it's only the remote end that needs additional sensors for the purposes of faulted section identification, let's say, and creating new electrical sections that you want to discretely monitor. So the critical thing here, though, is the security aspect. If you're not using any kind of fixed line or 4G telecommunications and you've got no data outside, is inherently secure and avoids a lot of those civil works challenges, leveraging the data network, which is the optical fiber, which was already there. Right. Sorry to go on about that, but I noticed that was a couple of the questions that needed explanation because we glossed over some of that terminology and some of those concepts. So I hope that's clear for everyone.
Sure. There's also a question here from Frank about traveling wave. Is traveling wave protection the technology of the future? So from my understanding, traveling wave is quite impressive, what it can do. I think, if I remember this correctly, I think it does have a blind spot though, where if the fault happens to occur at the zero crossing of the wave shape, then there basically won't be a traveling wave to detect. So I don't really know off the top of my head what the probability of that is, but there's some non-zero probability that that's going to occur. So I think it's a kind of nice supporting technology, but it's maybe not. It's not going to be the primary protection, or at least not. It could have a role in helping, maybe to accelerate protection, but I don't see it really replacing differential protection in the majority of cases, anyway.
I agree. I think there is not one solution that fits all the problems. So every problem must be tackled with the different tools, different solutions, and the traveling wave will for sure give benefits in where you need very high, very fast time. But the trip time doesn't need to be that fast anymore. If the network is getting weaker, the fault current will be smaller. You can keep the fault longer time. But the reliability in fault location, for example, for traveling wave is interesting. So traveling wave will have its own development in its own future, but it's not, unfortunately, never had any one solution for all the problems in relay protection technique. The solution is in the mesh communication networks. There's some good ideas, passive ideas. This one is a passive idea that in principle doesn't require time synchronization because the data is coming out as sample values from the same box. So they are already time synchronized by each other. But if you put this unit in the substation where there are other measurements, other merge units, then you need to be time synchronized. And I want to mention again that today process bus based on sample value solutions is requiring time synchronization. So time synchronization is a factor that it's a problem that must be solved. It's nothing you can make sure secret. In this case, if you use line diff only and your sensors, it's fine. We can skip the time skip, which is a very powerful solution, by the way. But in the longer perspective, where you integrate this system with other systems, we need to be time synchronized. And in fact, we tested that as well, the capability to manage, to deliver the data according to the standard.
Sure.
There's one more question here that might be interesting to explain, Stephen, which is about the so you slightly alluded to the speed of the system. Obviously, it's light speed coming back from the sensors, but sampling and publishing rates in terms of how we're interrogating and what we're publishing there synchronously. Could you just go through the options for that for everybody, please?
Yeah, absolutely. So from a single system, we usually can interrogate about 30 sensors per fiber. So if you need more sensors, you can scale up the number of fibers. And for protection, we typically sample at 4 kilohertz or 4.8 kilohertz. Or if it's more of a kind of measurement or power quality type of application, we can increase that to, say, 14.4 kilohertz, which is just governed by IEC standard for instrument transformers. So that's presently what we offer. In principle, we can go a little bit higher than that based on the technology stack that we have in hardware at the moment, in terms of what the interrogation of the light signals, how that's achieved in hardware. So our maximum bandwidth is, I think, approaches about 35 kilohertz. But in terms of the actual sampling rate that we deliver, 14.4 kilohertz is what we offer at the moment.
Stephen, if I remember correctly, that those are standards defined, right? That 4.8 and 14.4 is just something that's there by common agreement in the standard. I guess your point is that what we're trying to do is say that, well, we'll meet those standards, but if you're sampling and publishing at those much higher rates, whilst we're saying 4.8 kilohertz is perfectly fine for protection purposes over a wide area, a lot of our business is actually being generated by customers saying, well, great, while there isn't a fault, can you see anything which gives me earlier warning of some of those failure modes? And I guess that's important, isn't it? Because the higher the rate of sampling and publication of our data, then the more detail we're going to pass through. I'm thinking about harmonics and transients and other interesting things that would give you an early warning of an issue that you still might be able to avoid problems with.
Yeah, definitely. I think there's a lot of interesting things we're going to see with this approach, where we're able to deliver the waveform, the full waveform at each sensor location just by standard. There's nothing special done to achieve that. And it's effectively pulling all of these detailed waveform measurements over a wide area, bringing them back to a central location. So we're looking at some applications at the moment where we can analyze that high fidelity, high sample rate data, and maybe look for transients and apply techniques that haven't really been used before, because we have this centralized view of the system at the full waveform detail, and that could potentially lead into something that's a real-time system where it's picking up, things that are relevant for protection or control, such as oscillations, or it could be longer term, as you're mentioning there, Saul, about it could be looking at transients that indicate a particular failure mode of an asset, a primary asset in the system. So we're able to see that detail and perhaps learn it, and you use some kind of intelligent system to automatically detect future instances of that, to detect, when the lifetime of primary assets is in jeopardy, and perhaps provide a new route for maintenance of those devices that isn't really available at the moment.
Hey, I'm also just keeping an eye on time here before we wrap up, but we can take one more question here, and it's a stinker for you. So how was the sensitivity of measurement using this technology validated? How can we differentiate between a measurement and protection class?
Yep, so we do lots of testing of this in our own labs. We're using kind of standard test equipment in our lab. We're looking at the quality of the measurements and the timing quality as well. So for this particular application that we talked about today for SSEN, we validated that the system met the 5P performance requirement for the current measurements. At the moment, we're also we're looking into testing other types of applications like synchrophasor quality. We've already done some tests of that in software, but we're testing that with the hardware at the moment. So we're not fully all of the way there in terms of doing the standardization, the standardized validation that's required, but we spent a lot of time making sure that our protection measurements are highly effective. So that's a kind of partial answer, but there's still more we can do. But it's obviously we take it quite seriously when we're dealing with protection systems.
Okay, thank you for that answer. So Stephen and Andrea, just before we sort of finish up for today and say thanks to everyone, are there any other final comments or observations that are worth sharing with the group before we conclude today?
I was thinking about the cost for the smart grid. When we talk about smart grid, we talk about integrating different energy resources, communication. Remember that IEC 2050 standard is a core standard according to IEC for smart grid. And it's not that we don't know how to protect the smart grid. Yeah, there are new situations with the new waveforms, etc. But in high voltage networks, we have experience in protecting weekend, in feed, etc. So we are not completely blind in how to protect the smart grid, which is a lower voltage level. The problem we have, I think, in smart grid is that we have to use the high voltage technology, high voltage relay protection technology for the low voltage price, which means I cannot put one high voltage protection relay close to my solar panels because I had to pay for that, and I don't want to pay for that. As simple as that. And I don't want to test this relay protection every year because I have to pay for that as a private, and I don't care. I don't want to pay for that. So it's important that we give cheap and simple solutions to the smart grid community, and this is one, because if you can read my current from my solar panels at home and bring this information to the substation somewhere else, I don't care where you bring it. You don't disturb me. You can then take your trip decision in the substation and send the trip command to my breaker, if I have a breaker or music breaker, so that you clearly make the situation simple for me. I cannot have a substation under my solar panels. This is one of the limitations of penetration of smart grid in all the voltage levels, because we private people, we don't want to pay too much for that. And this type of solutions are what we need. Simple solutions, reliable, passive, as much as possible, but still they can manage the 650 standard, so they can manage a standardized way of thinking. So I was very proud to be able to participate to this project. It was interesting me from the beginning. I say thank you again for having invited me to the project and also to this short roundtable.
Thank you, Andrea. Okay, everybody. Very conscious of people's time. People want to get away now and probably move on to next meetings and grab a cup of tea or coffee between them. So just to summarize, we've recorded this session for everyone. We've taken a note of the poll answers and questions, and we've taken a note of some Q&A and chat activity. I do apologize. There were more questions. We still didn't get to them all. We won't ignore you, though. We'll follow up afterwards. Everyone who registered or attended this event will then get a follow-up from us to give you access, specific access to this recording, so you can review it at your leisure. It won't be publicly available. That's a bonus for people who are kind enough to give us their details and register for this event. Don't forget that on our website, so that's Synaptec, SYNAPTEC, with a dot between the T and the E, you'll find links to some of the case studies and white papers behind this stuff, and also recordings of prior webinars from last year, where there'll be more of these coming along. So again, thank you very much for everyone attending today. In particular, thanks to Stephen and Andrea for sharing some insights and some experience from this. We hope that subject area was of use to you. And if we didn't address what you needed to today, please drop us a line. Please keep in touch with us and let us know what you want us to talk about in upcoming events or in one-to-one conversations. We're always prepared to come to you and talk to you about your specific operational needs and how we help your business to save money, avoid outages and costs that are associated with wide area protection, monitoring and control. So thank you, everybody, and enjoy the rest of your day. I will just finish the session now, and we hope to see you all very soon. Bye now.
Thanks a lot.
Bye.